Welcome to Brain Vision.
So, welcome to a new problem. We have an astronaut in this time the astronaut is in a space station. So, in a space station, we have an astronaut, and they happen to have a mass. So, this is the information that you're given that the mass of the astronaut is 78.4 kilograms, and there is a can. Okay, assuming the can is floating and the mass of the can happens to be, we don't know what the mass of the can is. Also, the other information that we're given, well, this is a, a large, it's a gas canister. Okay, so we're going to call it um, mg, for example. It's a gas canister. And then, the canister is approaching the astronaut. So this is the canister, and this is the astronaut. So the canister is approaching the astronaut with an initial velocity of of 3.50 meters per second, um, and then she reaches out. Okay, so the astronaut reaches out and pushes it. Okay, and then it slows down. So it means that the canister, it's going to have a final velocity of 1.20 meters per second. Remember, the initial velocity of the astronaut happens to be 0 meters per second. And then once she pushes the canister, she develops some kind of final velocity. And the final velocity of the astronaut is 2.40 meters per second. So our goal is to find the mass of the canister. Okay, the mass of the gas canister. Uh, the law of conservation of momentum says that the initial momentum of the system is equal to the final momentum. So the initial momentum of the system equals to the final momentum, and the initial momentum of the system is the mass of the astronaut times the initial velocity of the astronaut plus the mass of the canister times the initial velocity of the canister, and that is equivalent to the final momentum of the system, which involves the final momentum of the astronaut plus the final momentum um, of the gas canister. Our goal is to find the mass of the gas canister. So we're going to move things around, and you get to see that we put all the information with the gas canister on one side of the equation, and then when you switch that, this one becomes a minus. This one becomes a minus because it moves to the other side. This one right here. Okay, it's going to move to the other side. So this is a minus mass of a canister, and then the velocity of the canister, and that's equal to the mass of the astronaut, uh, final momentum of the astronaut minus initial momentum of the astronaut. And the reason why the initial momentum of the astronaut becomes negative is because it shifts to the other side of the equation. That helps us to have an equation um, for mg. So this is ma. Uh, we can actually do it on the next page. So we have gas, a mass of canister, initial minus final. Okay, initial minus final. equals to, if you go back, mass of canister, final minus initial. Sorry, mass of astronaut. Mass of astronaut, final velocity minus initial velocity. And our goal is to solve for the mass of the canister. So this is MA, VA final minus VA initial. Always a good habit to keep your variables up until the end. It just means that you're going to be less likely to have computational problems. So then we plug in the numbers. The mass of the astronaut is 78.4 kilograms. And then the final velocity of the astronaut is 2.40 meters per second, minus the initial velocity of the astronaut, which is 0 meters per second, all over the initial velocity of the gas canister, which is 3.50 meters per second, minus the final velocity of the gas canister, which is 1.20 meters per second. When you solve that, you end up getting the mass of the gas canister, which happens to be 81.8, round about 81.8 kilograms. Okay, so 70, you can confirm that with your calculator. So 78.4 times 2.4, and then you divide that by 3.5 minus 1.2, and that gives you 81.8 kilograms. So that's the mass of the canister. Hope you enjoyed the question or the problem. Feel free to send any questions. Looking forward to the next one, and have a wonderful day. Okay, thanks. Bye.